start momentarily. Oh, it's already started. It's a tradition for me to do this. Hello, I'm David. So you've seen my face. You're not going to see it again in this revision seminar probably, so look good. Right, that's what I look like. You can imagine me talking to you now. I'm the coordinator of the Maths Learning Centre. It's my job to provide, well, to help people learn and to learn how to learn in any course where they're meeting maths, including ones with maths in the title, like this one, which is Maths 1B. It's Semester 2, 2019. Those of you watching from the future, hello from the past. And we're going to talk about Taylor series. I've just reminded everyone in the room that they get to ask me questions. You know, be a bit polite about it, but, you know, don't wait too long if you've got a question that applies to something that I just wrote. Of course, you watching online, you can't ask questions, but you could always drop into the Maths Learning Centre if you wanted. Okay, so Taylor series. Okay, so let me collect my thoughts about this. Right. The point of Taylor series is to write your function as if it was a polynomial, because polynomials are nice. They're nice. We understand polynomials. We know how many turning points they have. We can differentiate them easily. We can integrate them easily. That's the nice one. Other functions are hard to integrate. And, you know, they have a whole lot of useful properties. And polynomials are nice. And they're really easy to calculate in a computer what the answers are. So we would like it if everything was polynomials, but they're not. But we can pretend they are and approximate them as if they were close to polynomials, because all functions will be close to some polynomial, at least nearby to where you are. And that's the idea. So we would like all functions to be something like something plus, that's a 1, something x plus something x squared plus something x cubed, and possibly stop at some point in order to approximate it, but we want them all to be like that. Or we might not be interested in the actual x, but we might want to write them as if they were being measured around a certain point. A little bit like how a circle, you can write its equation not with an x squared plus y squared, but with like an x minus 1 squared and then a y minus 2 squared to put it in a different centre. So we could do it like that as well if we wanted, you know. Or so a0, a1, x minus c, a2, x minus c squared, etc. To do it in terms of the distance from C. Okay, so that's the idea that we're going to do. We're going to get any function we like, and we're going to attempt to write it like this. And it turns out that there's only one way to do that. And the only way to do it, so either it's the most accurate way to do it if you're going to approximate it, or the only way to do it if you're going to make this go on forever. The only way to do it is for these coefficients to involve the derivative of your original function. That's the idea. So the only way is for, you know, a0 to be f of c, and a1 to be f dashed of c, and a2 to be f double dashed of c divided by 2, and a3 to be f double dashed of c divided by 3 times 2, and a4 to be the fourth derivative with c subbed in 4 times 3 times 2. That's the only way to do it, which is nice, because it gives us a formula for how to figure out these numbers. So, I mean, you could totally, if you want to, just pick numbers and go, I reckon these numbers would make my polynomial pretty close to my function. But if you want the closest and if you want the best, then these are the coefficients you have to pick. All right. So, I'm just going to give an example of finding one. Okay? All right, let's find the fifth Taylor polynomial. Maybe not fifth, I should say like the fifth degree. I think that's how they say it. Just give me a sec. The terminology here is important. The fifth order Taylor polynomial for man, that's no, I've committed for x e to the x at 3. No, I'll do 0. 3's too hard. And do you know what? Do you know what? Right. Takes me a while. I mean, I'm coming up with this off on the fly, people. Cut me some slack. Though I did joke in the last seminar, how cool would it be if in the exam you could say, I don't like your question, I'm just going to change this to a 1. Okay. So this is what we're going to do. We're going to find this. So we have a function. This, when I say at x equals 1, this is the c that's being referred to. They don't always call it c. It's the grammar that tells you that it's the c. It is the location. There is going to be some phrase here that tells you that you're doing it at a place. So it might be with center c, or with center x equals 1, or at x equals 1, or around x equals 1. There's going to be some location phrase that tells you what the c has to be. Okay, so because of the at, I know that c equals 1. Okay. All right. So in order to do this, I'm going to have to find all the derivatives up to 5 because those will be part of the coefficients. So what I'm going to write is a degree 5 polynomial. It's going to have constant plus something times x plus something times x squared plus something times x cubed plus something times x to the 4 plus something times x to the 5. And I'm going to have to figure that out. So here we go. Okay. And the first derivative, product rule. Differentiate the x, keep the e to the x minus 1, plus keep the x, differentiate the e to the x minus 1, which would be the same multiplied by the derivative of that, which is 1, so it's all good. I tend to find that if it's got e to the x's in it, it's useful to factorise it. So, differentiate this, which is 1, keep the e to the x minus 1, keep the 1 plus x, differentiate the e to the x minus 1. So it's 2 plus x. Oh, I see a pattern forming. Okay, so I'll differentiate this and I'll get 2 plus 1. No, I won't get 2 plus 1, I'll just get 1, won't I? The 2 will become 0. 2 plus x. Aha! It looks like every time I do this, I'm just going to add 1 to this number here. All right, I'm just going to do it. So once I get to 3, your options for the fourth derivative are to write, you could write it in Roman numerals if you wanted, but most people put it in brackets like that. I've always been fond of the fifth derivative being that. You know, 1, 2, 3, 4, 5. Anyway. So that was less bad than I thought. It's very pleasant. Okay, and so I'm actually going to need all of these calculated at the center that I'm using. So I'm going to need them at 1. So normally what I do is actually I draw them in a table. So 1 times e to the 1 minus 1, which is 1 times 1, which is 1, okay? And then f dashed of 1 will be 1 plus 1, which is 2, times 1, which is 2. F double dashed of 1 will be 2 plus 1 times e to the 0, so that'll be 3, 4, 5. Beautiful. We're doing well. That worked out. I did not expect that to happen. That worked out rather nicely, actually. Okay. And we're still not done, because the actual coefficients we have, I'm going to have to divide these by successive multiplications of things. So this one's going to be as it is. This one's divided by 1. This one's divided by 1 times 2. This one's divided by 1 times 2 times 3. This one's divided by 1 times 2 times 3 times 4. This one's divided by, well, 5 factorial. So I will write the actual formula in a second. I really should have done it on the first page. Oh, I reckon I have room. That's the actual formula. The coefficient of x to the n is the nth derivative with c subbed into it divided by n factorial. Okay. Right, where was I? So I'm going to actually have to divide these by the numbers that go with them. So I reckon I can do that all in one go now. So my fifth Taylor polynomial, which in your notes is called T5x. So T for Taylor, 5 for which degree it is, which order it is going to be this number, which is the constant, plus this number divided by 1 factorial times x, plus this number divided by 2 factorial times x squared, plus this number divided by 3 factorial x cubed, plus this number divided by 4 factorial x to the 4, plus this number divided by 5 factorial x to the 5. Okay? 1 plus 2x plus 3 halves of x squared plus 3 factorial is 6. 4/6 would be 2/3. 4 factorial is 24. Well, that's not going to factorize with the 5. And 5 factorial is 120, which would be 1/20th. All right, there it is. Oh, crap. Yes. Thank you. So the fact that I forget that means that if I were in an exam, it would be one of my things I would remind myself to check. I would say, check at some point that you actually did the center properly. Right. Thank you. See? Good listening. Check that sort of thing while your lecturer is doing it, or it'll be half an hour away and it'll be too late. Okay. Important note, you don't have to expand this out. You leave it like this. Even if it was just a quadratic, you still wouldn't expand it out. You would leave it like this. The whole point of doing it with the x minus 1 is that you're not interested in what x is, you're interested in how far x is from 1, and so you want the formula to be that. So, yeah. So apparently, this function is quite close to x e to the x when x is close to 1. Now, you wouldn't be able to go to Desmos and do this in your exam, but we can do it here just to see what's going on. So that's what x e to the x looks like. I'm just going to take this.
Wasn't it x e to the x minus 1?
It totally was. Well done. Ah, stupid machine. All right. Similar. And the other function was 1 plus 2x minus 1 plus 3 over 2 x minus 1 squared. There it is 2. Well done. Plus 2/3 x minus 1 cubed plus 5 on 24 x minus 1 to the 4. Have you noticed every time I add a term, the function got a little closer? Five. So over here on the positive side, it's really close. We can't tell from the distance we're looking at that these are even different. It's pretty good for like about, oh gosh, about 0.1 on this side. Not doing a too good job on the negative side, but positive side, really good. Yeah. And it got better and better the more of those terms we added. That's the whole point of Taylor series. And if we zoom in, we wanted the point where x was 1. Oh, crap. If we zoom in, it's really good there. Like you can completely indistinguishable at Desmos's level of scale. No, still can't tell. It's really good. There you go. Okay. But it was pretty good even back here, right? So that's at the 4. That's at the 3. That's at the 2. It's really good close to x. But of course, if I get further away, it gets less good. Yeah, it should. There we go. Yeah. I mean, that's the whole point. The first derivative is pretty good at approximating your function. Yeah, so that got wider, the section that was good. Okay, sweet. So, that's finding a Taylor polynomial. That process, you have to find the derivatives, sub the centre in, divide them by their factorials, and then, write them next to the appropriate power of x minus c. If I gave myself enough space, I actually would have had a separate table for the coefficients. I would have put these calculations in here as they were. Right. So, I mean, it's nothing fancy. It is a little fancy, but it's nothing fancy. The whole point of doing these derivatives is to attempt to calculate what the numbers are that go next to these things. And they are the best numbers to choose because well, then the derivatives of this polynomial match up to the derivatives of the original function. And if that works, then it should be pretty close. Okay, but that's a particular Taylor polynomial. And we've noticed that it's quite close to the original. And we really would like to know exactly how far away it is, which is the whole point of the error term. But before I get to that, I do want to mention that we do have another idea that if I went forever, it should be equal to the function everywhere. Right? In the same way that 0.333333 is not 1/3, it's only 1/3 if I do the 3's forever. It's the same idea. This is not x e to the x minus 1, but it is if I did it forever. Same idea. So I would like to know, well, if I did do this forever, is there a formula for what this thing would be if I was up to a specific spot? And the answer for this one is yes, because I already guessed that formula based on the pattern that was going on here. I already guessed that the nth derivative was n plus x e to the x take 1, which means that the nth derivative at 1 is n plus 1, e to the 1 take 1, which is just n plus 1. And so therefore the coefficient of x to the n, which is this, is n plus 1 on n factorial. So the coefficient of x to the n in my Taylor series must be fn at the centre divided by n factorial, and fn at the centre was n plus 1, so I sub that in. And so that means, and I'm just going to check, sometimes this doesn't work back at the constant term. 0 plus 1 divided by 0 factorial is 1 divided by 1, which is 1. Okay, it's working back at the constant term. Sometimes it's different for the first couple. And so therefore I can say that x e to the x is that. I can write it with some notation because I have a formula for what that coefficient works out to be. Sorry? No, I didn't. Oh, yeah, there. Right. I didn't forget it here. I didn't forget it when it was important. Okay, cool. So this is called the Taylor series at x equals 1 for this. Yes? Because it's x minus 1, and I have subbed in 1 for x. This was x, now it's 1. This was x, now it's 1. And 1 minus 1 is 0, so e to the 0 is 1, and so I'm multiplying by 1, so it's n plus 1. Okay, so this is the Taylor series for x e to the x minus 1 at x equals 1. And when we say Taylor series, that means it's the one that goes on infinitely many terms, as opposed to Taylor polynomial, which has to stop at some point. Right. So this one had a particularly neat little pattern, which was nice. It was easy for us to see what the pattern was doing. Some of them, it's a little harder to see what the pattern is doing. Yeah, and I'll do one of those in a minute. Okay. Oh, I'll leave it. I can move it up a bit though, right? Now, all of these notes will be on the Maths Learning Centre website afterwards, and I'll send you an email to say where they are. Okay, and by afterwards we mean at some point tomorrow, possibly the next day. because I'm in 3 revision seminars tomorrow as well. Okay, so that's the general idea. The next question we would like to ask is, how close is our Taylor polynomial to the actual answer? So when we had our graph before on the screen, there were some places where you couldn't tell the difference, and it was very, very close. I mean, it's never actually equal usually. And there were some places where it was not close. And it was really bad. Yeah. Okay, so you know it's always exactly the correct answer at the center, like at the value of c that you're looking for, because you set it up that way. And you would like to know, if I pick a specific x, can I figure out how far away the real function is from the Taylor polynomial? That's what I would like to do. I mean, obviously, if I draw them, I can actually calculate that distance myself. But the real reason you want to do this is usually because you want to say, well, what power should I go to? Like, what power of x minus 1 should I go to in order to get it close enough for whatever purposes I'm interested in? So, for example, I might say, what power of x should I go to in order for Desmos to look like it's the same graph? So they need to be within, 1 pixel's distance, right? Something like that. So that's a question I could ask. And I know that it was pretty good once I got to 5, but that was just me trying it, right? I want to calculate just how far do I have to go. And for that, I need a formula for how far apart they are that doesn't involve me actually calculating the actual Taylor polynomial. Because otherwise, what's the point, right? I could just calculate the Taylor polynomial each time. So that's what I want to do. And the reason we care about that is sometimes, based on other reasoning, we can figure out what this formula should be without having to do all those derivatives. And so if we can figure out how far to go, we can just write down the one we want. Okay, that's the philosophy. So I'm going to write that down. How close the Taylor polynomial is to the actual function. At each x. And usually it's only at 1x that I'm interested in. And I want to be able to do it without having to calculate the actual Taylor polynomial. And that's the important bit. And so Taylor, that Taylor polynomials are named after, Taylor has a theorem. I think it's actually Taylor and somebody starting with L. Just let me have a second. What? Why are we doing L'Hopital's rule now? Where is it? This is why you have an electronic version and a paper version. It's the electronic version, you can search it. Contents, let's... Okay, so that's Taylor series. I'm looking for something that has, aha, there it is. Taylor's remainder. Okay, cool. They still call it Taylor's remainder in this. Some courses there's another person's name there. Okay, so what Taylor figured out was that he couldn't figure out exactly what it was without actually calculating the Taylor polynomial, but he could figure out approximately what it was. He could figure out that it couldn't be any worse than something. He could figure out that it's possible, theoretically, to find it without finding what Tn is. And therefore, you could say, well, it can't be any worse than this. And so this is Taylor's actual theorem. So Taylor's theorem on remainders says that if Tn, the nth order Taylor polynomial for fx at x equals c and fx equals tnx plus the error, like that. In some places on the internet and in some of my past revision seminars, they use an R in that spot for remainder instead of an E for error. Just letting you know. So Enx is the space between the Taylor polynomial and the actual real function. Then the error is the n plus 1th derivative of x calculated at the location psi. Your lecturer probably called this z. Stupid. Yeah. All the other Greek letters we call something I in English, so it's got to be something I. And it doesn't make a z sound, it makes a x sound. So it's xi. That's what I call it anyway. I'm sure in modern Greek it's called something else entirely. Okay, xi, xi. So xi x minus c to the n plus 1 over n plus 1 factorial. So that is Taylor's theorem. Oh no, it's not quite finished yet. Just a second. For some psi between x and c. Right. I can write a letter psi nicely. All my other letters are crap, but this one I can do. Okay. So there's a lot going on in this theorem. So the first part of the theorem is just setting it up to say, well, we've got a Taylor polynomial, and the error is what you have to add to the Taylor polynomial to get the actual function. So if your Taylor polynomial is below the real function, then the error is positive. If your Taylor polynomial is above the real function, then the error is negative. Yeah. Some people define it the other way around. Whatever, it doesn't really make much of a difference. Okay. And what Taylor says is that what you do is you do this calculation, the same calculation you would do to do the next term of your Taylor polynomial, because, you know, it's exactly the same as this here, except instead of c, you pick some other number. And there will be, if you pick the correct number, there will be a number you can pick so that this is the right answer. But the problem with the theorem is that Taylor doesn't tell us which number to pick. He says it's one of the numbers that's somewhere between the x you're thinking of and the c. And it will be a different psi for every x. So each x will have a different psi. So it's really quite frustrating. We actually have no idea, right? I mean, but it's not, I mean, not no idea, because we can use it, because if we have an idea of how big this answer might work out to be, if we go, well, we don't know which psi it is, but if we look at all the psi's between x and c, and we work out what the biggest answer this could possibly be is, then you know that the error can't possibly be any bigger than that. And it's got to be smaller than that. That's the idea. So let's actually do that with my example here. I always forget to put a capital. Okay, let's find that for the Taylor polynomial earlier, which was for f of x equals x e to the x take 1. Okay, so what we can do is we can figure out the error, and remember that this 1.2 is that, or at least find an upper bound for the absolute value of that error. That's normally what you're asked to do. So how far away is it? I don't really care if it's above or below. I just want to know the size, so we put the absolute value on. And when they say an upper bound, they're saying, well, upper bound means a number that is bigger than this. I mean, obviously you could say 10,000. It's definitely smaller than that. But we'd like to be more precise than that. And so, yeah, more precise. Okay, so E5 at 1.2 will be the sixth derivative at some number psi. I always make that loop a bit too long. 1.2 minus the centre, which is 1, over 6 factorial. That's what it is for some psi between 1.2 and 1. Okay. Now, but I know what the sixth derivative is. I had a formula, I had a pattern for that. The sixth derivative came out to 6 plus x e to the x minus 1. Now, f6 of x was this, like that. And so therefore, f6 of psi is 6 plus psi e to the psi minus 1. Cool. Yay. Okay. So here's the thing. All the rest of this is just a fixed number. Like that's 120. That's 0.2 to the power of 6. So this, whatever this number works out to, this number works out to be, is dependent on what this works out to be. So if I want to find what the biggest possible option for what this could be is, I should find what the biggest possible option for what this could be is. So I need to think about, for all of the numbers that I have to choose from for what this psi could be, I need to pick one that makes this answer the biggest. Okay. Well, 6 plus, if I was using x, 6 plus x is an increasing function, like y equals 6 plus x. And e to the x take 1 is also an increasing function. So this is an increasing function. So the maximum value is when psi is 1.2, because that's the biggest number I get to choose. If it was a decreasing function, the maximum would be at 1. And if it both increased and decreased, I would need to figure out where that maximum actually was. Now this is pretty sad, because the whole point of calculating this was to approximate x e to the x take 1. So if I have to calculate what number times e to the number minus 1 is in order to approximate number times e to the number minus 1, it's a bit stupid. Like if I have to know what e to the x minus 1 is to approximate e to the x minus 1, what? So what we're going to have to do is approximate it even further. And so what we're going to do, it's an increasing function, so the max value is here. And we can say, well, this, well, let's just think about that. Okay, so we know that this is certainly less than this. Like that. And so that's 7.2 e to the 0.2. And e to the 0.2, that's like a fifth, right? It's like the fifth root of e. And e is less than 3. Fifth root of e, it's got to be smaller than e. It's got to be pretty close to 1, I reckon. When you do a whateverth root, it gets closer and closer to 1. So I'm thinking that the fifth root of e, well, it's got to be less than the square root of e, and the square root of e is less than root 3, and root 3 is about 1.7. So I'm thinking this is less than 1.5. That's when I go. That's a pretty rough estimate. Most people would have just stuck 3 in that spot. It's definitely less than 3. E is less than 3, and e to the 0.2 is less than e. But I'm going to choose that. And so, yeah. What's 1.5 times 7.2? 1.5 times 7 would be 7 plus 3.5, 10.5. So 10.5. 1.5 times 2 would be 3. So 10 point... This is what calculators are for, of course. Right. That doesn't seem right. I think, that's what calculators are for. It was right? No, 10.8. I like practicing my mental arithmetic. I'm pretty bad at it, so I like to take my opportunities to practice it. Well, maybe I should update it. I'm not as bad as I say I am. Okay. And so therefore, E5 of 1.2 is less than 10.8 times 1.2 minus 1 to the 6 over 6 factorial, which is 10.8 times 0.2 to the 6 over 120, which is actually a shockingly small number. And it's okay to just do ordinary calculations like that. 10.8 times 0.2 to the 6 divided by 120. What? Oh, 1, 2, 3, 4, 5. Yep. No, 6 factorial is 720. 5 factorial is 120. Oh, that means my answer earlier was wrong. Yeah, oh gosh. Sorry. All right. It's too late now. Really, no one cares.
No, you had it right because it's 6 on 5 factorial.
Oh, it's all right. Okay, it's all good. It was right before. Yeah, start second guessing everything once I find some errors. Okay. It's gotten small enough for my calculator to give it to me in scientific notation. Ten to the minus 7. Beautiful. So the error is really small at 1.2. which it should be because our graph said it was really close. So, yeah. So the fact that it's 10 to the minus 7, if it was 5 times 10 to the minus 7, that would be 6 decimal places. So we've got 5 decimal places. Six decimal places is 5 times 10 to the minus 7. Yeah. Great. Cool. So 5 decimal places is small enough for us to not be able to perceive the difference with the naked eye on Desmos. Okay. That's that. But then the next thing we'd really want to do is to be able to do this from scratch with a new function. So let's go. So what is the smallest n so that Tnx for f of x equals, what do you reckon? I don't know, sine 2x or something? Let's do that. Is accurate with center do we do 0 this time? Yeah, let's just make life easy for ourselves. I mean, we could, no. Is accurate to 3 decimal places for all x within, I don't know, when Tn pi 3 is calculated. Let's do that. Okay, so we know what the answer for sine of 2 times pi on 3 should be. It should be sine of pi on 3, which is root 3. So it should be about 1.7. Yeah, sine goes big when the angle's big. That doesn't really help us any, but it's just a good thing for me to try and figure out. So I want to know, when I calculate this, what does n have to be to get it close enough to within 3 decimal places of the correct answer? So you could, conceivably, it's not very big, you could just find some Taylor series and try them all and see which one gets there. But I want to do it the proper, in inverted commas, way, using the Taylor's error formula. So to find Taylor's error formula, I'm going to need to find the n plus 1th derivative. So f of x is sine of 2x. F dashed of x is cos of 2x with a 2. F double dashed of x is 2 squared. Sine of 2x but with a minus. I should not have chosen sine. This is going to be confusing, but that's okay. Sine will still be a cos, and another 2 will get multiplied on. And then the cos will become a minus. Okay, and we're back to the beginning now. And so the power of 2 is going to keep going up, and we're going to be cycling between sine and cos and minus sine and minus cos forever. That's hard. So depending on whether n is a multiple of 4 or a multiple of like, so every multiple of 4, so this was 0, 1, 2, 3, 4, it'll be sine again and it'll be positive. And whether it's multiple 4 plus 1 or plus 2 or plus 3 or plus 4 will change what it is, sadly. But that's okay. But what we do have is that the nth derivative is 2 to the power of n, definitely. The 4 had 2 to the power of 4, the 3 had 2 to the power of 3. Yep, and it's either going to be plus or minus 1, plus or minus, possibly one of those, and it'll be sine or cos. One of those. That's what the nth derivative is going to be. One of those 4 things. And we're saying, but David, that's a lot of options. That's okay, because we don't need to know. We just need to know what it's less than. Okay? It's a really cool trick. We don't need to know what it is to find the error. We only need to know what it's less than. So if I was going to try and find the actual Taylor polynomial, that'd be so painful. But if I just want to find the error, that's a little easier. Okay? Because I just need to know what this is less than for the psi I'm interested in. So we'll get to that in a second. So we know that the n plus 1th one, which is what we really needed, has an n plus 1 in that spot. That's what we need to know, which means that the error at the point x is one of these things. But I'm not going to put that in. Okay, that's what the error is going to be, because the centre of my Taylor polynomial is 0. And this is going to be for between 0 and pi on 3, because that's the place I want it. Okay, so I would like to know, what does n have to be for this thing here to be less than what it needs to be 3 decimal places? And so if I knew what this was less than, and I made the thing that's less than 3 decimal places, then this would have to be less than 3 decimal places. I will describe that again on paper in a minute, so it makes more sense. Right. The issue is going to be this thing. I need to know what this is less than. And I don't really care about this. I just want the error, absolute value of the error. Right? N is a positive number. Pi on 3 is positive. So we've got this. Well, here's the thing. Let's have a look at what this absolute value is. But the absolute value of f n plus 1 psi is either going to be, well, it's one of these things, and the plus or minus is going to go away when I do the absolute value. I don't need the minus anymore if I've done the absolute value. So it's going to be 2 to the n plus 1 sine 2x, or 2 to the n plus 1 cos 2x. Oh no, sorry. Psi. Right. So that's those things. Now here's the magic trick. I don't care what psi is, because I know that sine of anything is always less than 1. And I don't care what psi is because I know that cos of anything is always less than 1. Well, less than or equal to. And so because sine and cos are always less than or equal to 1, I know that this thing must be less than or equal to 2 to the n plus 1 times 1. And so therefore the absolute value of En is less than or equal to this. That. Right. So, what this tells me is that. And what I need to do is I need to arrange, if I arrange for this thing to be less than 3 decimal places worth of difference, then this will have to be less than that as well. And so I can say this. So sorry, just a second. 3 decimal places would be 5 times 10 to the minus 4. That's the difference between numbers that are 3 decimal places accurate. The reason of that is that the thing that tells you how to round off to 3 decimal places is the 4th decimal place. And if that 4th decimal place is less than 5, then you round off to the same number you had before, which is why the 5 times 4th decimal place. Okay, and that's what we need to do. Cool, huh? Okay. I guess I can do this. This is where you actually usually have to do a bit of trial and error. So I know that factorial grows faster than powers do. And so it should come at some point where this is bigger than that. I'm just going to need to estimate when it's a lot bigger than that. So 2 pi on 3 is about 2. Pi is about 3. Pi on 3 is about 1. So 2 pi on 3 is a little bit more than 2. So I need to figure out the point at which 2 to the power of something is a lot less than thing factorial. So, well, 6 factorial is 720, and 2 to the power of 6 is 64. So we're not quite at the 10 to the minus 4 yet. So 10 factorial is frelling huge, and 2 to the 10 is only 1,000. So I'm going to guess 10 and ask my calculator. So 2 times pi on 3 to the power of 10 divided by 10 factorial. All right, we're actually exactly at the right spot. That's 4 times 10 to the minus 4. We're now just less than 5 times 10 to the minus 4. That was a great guess. Otherwise, you just keep trying them until you got below the point you wanted to. That was a really good guess. And so that happens when n equals 9, right? Because it's actually n plus 1 here. Let me just check what it is at the previous one. All right, yep, we definitely need to go all the way to 10. So we need n to be greater than or equal to, because that there is like 9 plus 1. So we need n to be greater than or equal to 9. So, I mean, the finishing of the argument is that if this is less than 5 times 10 to the minus 4, then en is going to be less than that as well, because e to the n is less than this. So just let's finish it off properly. So the ninth one is less than this number. So we know that it's the ninth one is less than this or equal to this number. And we know that that number is less than 5 times 10 to the minus 4. And so therefore this is less than 5 times 10 to the minus 4. And so yep. All right, there we go. So this part here is a bit of trial and error. And I would actually just write trial and error. There are times when you don't have a factorial in this spot and you can just make a guess. You can actually solve it with logarithms. But with the factorial, it just gets worse. And so I like to reason about powers that way. But then I happen to know the factorial is up to 6. That's sort of when I get, yeah. And I also know that their digits grow pretty fast. Like 100 factorial's got 169 digits. It gets pretty big. I know about that because our puzzle solving session every week is called 100 factorial. So I know a bit about that number. Okay. That's enough of Taylor series error formulas, I think. Oh, except one thing. There are 2 Taylor series, 3 Taylor series, 4 Taylor series, sorry, that you're supposed to be able to know off the top of your head without having to do any of the derivatives. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial, no matter what x is. It takes longer to get there when x is positive than it does when x is negative. But it works. So this is a Taylor series with centre 0. Cos x is the same terms from e to the x, but the even-powered ones. And they alternate between plus and minus. So I take my x to the n over n factorial, I put 2n instead of n so that it makes it an even number, and then I do minus 1 to the n. And sine x is the odd ones. I'm pretty sure you're supposed to remember those. You're definitely supposed to remember the one for e to the x. And there is one more Taylor series. Oh crap, there's 2 more Taylor series. Sorry, that you're supposed to know. One is this one. Is that 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. And you know that one because it's a geometric series this side. Okay, And there's one more, which is the binomial series. One plus x to the power of k, where k is any real number. Is k choose n times x to the n, where we have a new and special definition of what like 2.5 times choose 3 means, which didn't exist before because it's stupid. But what we've done is we've created a new definition of what this symbol means when k isn't a whole number. And this symbol means, it's easier to do as an example. Just as an example, 3.5 choose 2 has on the bottom 2 times 1, same as it used to. This is 2 factorial on the bottom, and on the top it starts with the 3.5 and then it goes down by 1 and has the same number of things on the top as it does on the bottom. And 1/2 choose 3 is 3 times 2 times 1, and then on the top it has a half, and then you take off 1 so you get minus a half, and then you take off 1 so you get minus 3 on 2. And there are 3 pieces here just as there are 3 pieces here. And these go down by 1, and these go down by 1. These are the series in your neighbourhood.
Do any of the series change depending on where you're centered?
Yes. So if you wanted e to the x centered at 1, for example, these are all center at x equals 0. If you wanted your center at x equals 1, now here we go. Nothing up my sleeves. E to the x is this, right? And I would like this to not have x to the n, but to have x minus 1 to the n, right? So I'm going to arrange for there to be an x minus 1. Ready? Now there's an x minus 1. And this is the same as e to the x minus 1 times e to the 1, which is e to the x minus 1. And the e to the x minus 1, well, e to the x is this, so it still works if x is x minus 1 instead. So I'll just sub x minus 1 into this instead. And there we have it. Taylor series for e to the x centered at 1. Magic! It's beautiful. Okay, so that's one of the tricks that you can use. I don't know if your lecturer wants you to do this in this course, but it's a classic thing that they use in later courses. The Engineering Maths 2Bs, because that course won't exist next year, they'll have a new course, but the complex number calculus students have been using that fact in this last week. I think that's enough of Taylor series now. Okay. All right. So just a second. What did we do there? Just want to sum that up. So we said that the whole point is to write a polynomial. It could go on forever. The only way to do it is to do this calculation to figure out the coefficient. And the way to do that is to find all the derivatives, sub them in, divide by the factorials, and you've got it. We can sometimes make a guess at the pattern that's going on and be able to create a formula for what goes in this position. And then there's this remainder formula which uses the next derivative, and there's a few little wiggly bits where you're trying to figure out what that is. And then there are a couple of Taylor series infinite ones that you're supposed to just know. I mean, if they say derive this, then you have to do all the derivatives. But if they say what is it, you can just write it down. Okay. Sweet. Okay. That was Taylor series. Where are we up to? When am I supposed to finish this? past. Okay. I shall talk about, well, I'll do an algebra thing, eh? So, out of the algebra things, I'm going to ask you to choose 3 things. Would you like me to talk about, just give me a minute, these are the 3 things: Gram-Schmidt, linear transformations, or singular value decomposition. And so, if you want me to talk about singular value decomposition, pop your hand up. Okay, that seems almost decided. If you'd like me to talk about linear transformations, put your hand up. That's some of the same people. Great. And if you want me to talk about the Gram-Schmidt process, pop your hand up. Okay. Well, I've never done one on... I've done one on linear transformations before, and the Gram-Schmidt process before. So if you're looking for it, it's on the Maths Learning Centre website, and you can always come to the Maths Learning Centre and we can chat to you about it there. But I can make an attempt to talk about singular value decomposition. But I do want to check something. Did your lecturer say words to the effect of singular value decomposition is not going to be in the exam? No? Okay, just checking. That would have been nice. Have they told you what level of things that you're supposed to know for the exam?
He says anything that he talks about in lectures, but if it's in the course notes, but he doesn't talk about in the lectures.
Okay, so he did talk about singular value decomposition in the lectures. Good to know. So I warn you, I'm making this up as I go along. I've never done a revision seminar on SVD before, and I've never studied it myself as a student. However, I'm really good at figuring stuff out. So, my understanding of this goes something like this. First, there is a thing called orthogonal diagonalization. So if the matrix A is a symmetric matrix, you can find an orthogonal matrix P such that P transpose AP is a diagonal matrix. And that's called orthogonal diagonalization. So that process of finding the P and figuring out what the diagonal matrix is called orthogonal diagonalization. Ordinary diagonalization has a -1 in this spot instead of a transpose. Orthogonal diagonalization has a T in that spot. And when we say orthogonal matrix P, we mean a matrix where P transpose is the same as P inverse. So this is technically ordinary diagonalization because the P transpose is really P inverse. It's just that only some matrices, in particular the symmetric ones, allow you to do it so that you can put a P transpose in that spot. And that's called orthogonal diagonalization. And it's nice and it allows us to do things like transform coordinate systems in physics and to figure out what the most important factors that affect an outcome is in statistics and other stuff like that, which is why they have it in Maths 1B. Okay. But, oh no, wait. Before we finish that, it turns out that if you want to do this, that the matrix P is made up of eigenvectors of the matrix A. It turns out the columns of P are eigenvectors of A. And not just that, in order for this trick to work, they have to be also an orthonormal basis for Rn. I mean, they're orthonormal to each other. And also, the diagonal matrix D, which is P transpose AP, has the eigenvalues of A on the diagonal, which is all pretty cool stuff, right? So what that means is that technically, if all you want to do is find out what the matrix D was, you wouldn't have to find P at all. You just need to find the eigenvalues. Yay. But if you did want to find the matrix P and you found it, you wouldn't actually have to do the multiplication because you'd know what it would come out to anyway. So you don't need to do it unless you really wanted to check it was doing what it was supposed to do. Okay. So what if we wanted to do this for matrices other than symmetric matrices? Because, you know, most matrices are not symmetric matrices. There are lots of situations in which you make a matrix, you can arrange for your matrix to be symmetric anyway. And so that's okay. But, you know, and what if it wasn't even square? Because this whole thing only works for square matrices. And thus is born singular value decomposition, according to what your notes seem to say. So with singular value decomposition, we want to do a similar trick. We want to somehow multiply our matrix on one side and on the other side so that it becomes a matrix that has numbers down the diagonal. So singular value decomposition for which I will need the algebra notes. Oh, for the sake of frail people, why are you doing this to me? Okay. It's okay. I'm going to write this slightly differently because I want it to match up. Just a second. Okay. Okay, so we're going to do the same trick, but we're not going to be able to do it with the P and the P transpose being the same matrix. We're not going to be able to have this matrix being that matrix transpose. But we are going to arrange it so that we can do it. So we're going to have that A is going to be equal to U transpose. No, just a second. So note, A P transpose AP is the diagonal matrix D, which means that if we multiply it this way, multiply P on this side here and here, then we'll get a PD, but the P times P transpose is the identity because P and P transpose and P inverse are the same. So we get that, and multiply a P on this side, P transpose on this side, we get that. Okay. So instead of thinking of this as a process which turns A into a diagonal matrix, we're going to think of it now as a process which turns a diagonal matrix into A. Okay. Now we'll do the singular value decomposition. It would have been really cool if we had done it as PDQ transpose or something like that, so that the letters matched up more nicely, but they don't. So this capital sigma here is playing the role that D used to play when we did orthogonal diagonalization. And this is playing the role that P used to play. And this is playing the role that P transpose used to play. So when we did orthogonal diagonalization, the P and the P transpose were the P transpose was the transpose of P, but in this one, V transpose is not necessarily the transpose of U. So not necessarily true that U is equal to V. Okay, and I imagine that it's called sigma because sigma makes a S sound and S for singular. In the same way that we use a capital sigma for sum notation and it's S for sum. Yeah. Pretty weak. Okay. Okay, so that's the plan. And it may be that these matrices are, that the matrix sigma and the matrix A are not square. But I'm pretty sure that the matrix sigma and the matrix A are the same size as each other. Yep. So just some notes. If A is m by n, then sigma is m by n as well. And U will have to be m by m, and V will have to be n by n. I can't think about that in that notation. I'm actually in my head thinking of this. So all the edges have to match up correctly, right? So this m here has to match with that m there, and this n here has to match with that n there. So the U and V are not just necessarily not the same matrix, they're not even necessarily the same size. They might be different sized matrices. Okay. So also it's very important that they are still orthogonal matrices. Meaning that U transpose is the same as U inverse, and also meaning that the columns of U are an orthonormal basis for whatever they're an orthonormal basis for, and the columns of V are an orthonormal basis. And that's why we still write V transpose here, because there's no particular reason why you would call just a matrix transpose. You could just give it a name. The reason we call it V transpose is because the rows of V transpose are orthonormal. And we're not much more used to thinking about the columns of matrices than the rows, and so V transpose is focusing on the fact that it's about the rows of that matrix. So, yeah. Okay, so that's the goal, and apparently there's a magic trick in MATLAB that will do it for you. Some clever person who understands singular value decomposition has programmed a computer to do it for you. If one day, for no reason, you woke up and there was no MATLAB, you would have to program it yourself. And so it would seem reasonable that you would have to know how singular value decomposition works. Of course, that's not going to happen, but it's a little, you know, the movie Yesterday where he wakes up and the Beatles never existed? It's like that, right? You wake up and there's no MATLAB, and so you have to construct MATLAB from your own memory and make lots of money by selling it to universities. Anyway, it's not as compelling a movie. All right. Okay. So I think that's part of the point. If you understand it, then you can make it yourself, or you can at least understand how it's made and whether it's doing the job it's supposed to do. But sometimes I just think that people in lectures tell you things because they think it's cool. And it is, sort of. There are some things I think are awesomely cool which you won't think are cool. Like, eigenvalues are just fabulous, like, honestly. And the Cayley-Hamilton theorem is, wow! But you might not think that. But singular value decomposition, I haven't spent enough time with it to really get to know it, to decide whether I like it or not. Okay, so as far as I can tell, there's some nice little magic tricks that go on, which say that sigma ends up, its diagonal means it's 0 everywhere except on the main diagonal coming down. And the entries that you get down there are called the singular values. So suppose you got your A and it came out to this. Just as an example, then these numbers here, the 3 and the 2, are called the singular values of A. I don't know. I'm pretty sure it said, oh yeah, sure. The 0 is as well. Color code. Give me a second. No, it specifically says in your notes that it's the non-zero entries that are the singular values. So not that one. Just the non-zero ones. That's what it says. See? There it is, non-zero diagonal entries. Oh, but then, bloody hell. Now it says the non-zero singular values, but why would you tell me they were non-zero if we chose them, if they can't be 0? Oh, honestly, people. Well, other corroborating information here is that they say that the singular values are the square roots of the eigenvalues of A transpose A. Now A transpose A can totally have 0 eigenvalues. That's totally possible. And if it really is the square roots of those, then 0 is a possibility. So I have two things that indicate to me that 0 is possible as a singular value, and so I am going to take that as the possibilities. But it would not be the worst thing for someone to jump onto the discussion board or something like the forum and ask the lecturer, are singular values allowed to be 0? Because the lecture notes seem to contradict this, seem to give two contradictory information. If they answer, please drop into the Maths Learning Centre and let me know. Okay, so it turns out that if it's even possible to do this, the only way it's possible to do this is to have the same set of numbers in these positions every time. They might be in a different order, but they'll always be the same numbers. No matter which u and v you find that will achieve this trick, these numbers will work out to be the same numbers, which is a beautiful magic trick. Okay? So and so that's why they are called the singular values, because there's only one collection of them. And the real magic trick is it turns out that these numbers are the square roots of the eigenvalues of A transpose A. So there's a theorem. It doesn't say it's a theorem, but if the eigenvalues of A transpose A are lambda 1 up to lambda, just a second. Just a sec. So A was m by n. A transpose would be n. There are n of them. Okay. There are the same number of them as there are columns of A. Then the singular values of A are that. So A transpose A is an n by n matrix. It has n singular values. So the singular values will be the square roots of those. Now, interestingly, if A has more columns than rows, there'll be more of those numbers that can actually fit in here. So I think actually now I have more evidence that says that actually the non-zero ones are the ones that we care about. Damn it. We're going to need to decide this. I'll just put a question mark there. I don't know. I think that if this is true, this matrix here has more columns than rows. And so when if I do A transpose A, that's the same size as this. A transpose A will be a 4 by 4 matrix which will have 4 eigenvalues and therefore 4 square roots. And we can't fit 4 things on this diagonal. So one of them is going to have to be ignored. And so they can't be all of these. I reckon they must be the non-zero ones, the singular values. Your lecturer has actually defined the singular values to be these numbers. So I think the singular values are not these numbers. The singular values are actually these numbers. Okay. I'll write eigenvalue as E value if you don't mind. Okay. So it seems to me, just based on putting all these bits of information together, that people in the past have had a bit of trouble deciding what the singular values are. They must have, or we wouldn't have all these contradictory bits of information. And so what they did is they went, we've got to make a decision, and our decision is that these numbers are the singular values, the square roots of the eigenvalues of A transpose A. Sweet. Okay. So I suppose that your lecturer hasn't explicitly shown you how to figure out what the matrix U and the matrix V are. And so you don't need to do that. But you do need to know how to find the singular values. So if you had a matrix, you could find its singular values by finding the eigenvalues of A transpose A. So let's just do one. Let's see what happens. I have no idea. This could turn to utter crap. And therefore, I'm going to put an extra 0 or 2 in here just to... Yeah, one more 0 and smaller numbers should hopefully make it not too horrible. Okay. So A transpose A, the first row of A becomes the first column of A transpose, the second row of A becomes the second column of A transpose. A is this. Okay. I couldn't do transposes of non-square matrices until I figured out that thing of row becomes column, row becomes column. I was trying to do things with flipping and over and it just didn't work. Okay. So 1 times 1 plus minus 1 times minus 1 is 2. 2, 0, 0 minus 3.
0 minus 3.
No, it's 0 minus 3, which is negative 3. Yep. 2 times 1 is 2. 0 times negative 1 is 0, so that's also a 2. 2 times 2 is 4, plus 0 is 4, sorry. 2 times 0 is 0, 0 times 3 is 0, 0 times 1 is 0, 3 times negative 1 is negative 3, 2 times 0 is 0, 3 times 0 is 0, add them together, still 0, 0, 9. Which is a symmetric matrix, as it should be. A transpose A is always a symmetric matrix. So actually, technically, I could have just known what these two were without calculating it because I already knew what these two were. Yeah. A transpose A will always be a symmetric matrix. And a symmetric matrix is nice because the eigenvalues of a symmetric matrix are always real. No. So I'm doing lambda I minus A transpose A now to find its eigenvalues. Oh, man. All right, yeah, I've painted myself into a horrible corner. Yeah, that's just yucky. I could expand it along the bottom row. That's got a 0 in it. I guess if I did some row operations, I could get some other zeros. But, you know, it's not going to be nice. Plus, minus, plus 3. Minus 0 times thing, plus... I can totally imagine a really nice exam question where a lecturer in part 1, like in question 1, said find the eigenvalues of the matrix B, and then question 2 said find the singular values of the matrix A, and then when you did A transpose A it turned out to be B and you'd already have done it. That would be the sort of thing that would be kind of cool. Okay. So 2 times 0 is 0. Yep, I don't like my chances of factorising that. No. Nope. This is the point at which I would say it's a lost cause without a machine to help me factorise this. And so I will say whatever the solutions to this equals 0, square root them, that's the singular values. All right. Is it a lost cause? Let's see if we can change it so that we can get an answer. Yeah. I just want to do one more thing. Just to... No. Just trying to guess. So there's a lambda minus 4 there, but then it's like plus 5 of this. And this doesn't, lambda minus 4 doesn't go into that. No. Damn it. Right, no wonder it takes people months to write exams. Okay. I am just going to ask a computer to tell me what the answers are. We wouldn't be able to do that in our exam. But sometimes, you know, they do things like, you know, find the singular values of this. For your information, the zeros of this polynomial that you think is random is this. And then you go, well, it's not that random. That must be the polynomial I'm looking for. Oh, one of them is 0. Really? Wow! We might be able to do it. Really? Oh, that's so cool. Okay, just a second. So that would mean that if I put 0 into this, it comes out to 0. So, whoa. Yeah, yep, sorry. So 9 times 4 is 36. And 9 times 4 is minus 36. Oh, wow. I would not have guessed that at all. Oh, that's so satisfying. So that means that these columns are linearly dependent. If one of the eigenvalues is 0, the matrix isn't invertible, which means the columns are linearly dependent. So, yeah. Okay. So since lambda equals 0 is one of them, it must be possible to factorize this, so it's probably worth actually expanding that out. Minus 9 lambda plus 36 plus lambda cubed minus 6 lambda squared plus 4 lambda minus 9 lambda squared plus 54 lambda minus 36. Oh, it's beautiful. So we've got minus 15 lambda squared and the lambda cubed as well. So lambda cubed minus 15 lambda squared. 54 plus 4 would be 58, minus 9 would be 49. And then a 0. Oh, I'm so excited. So we've got lambda equals 0. Not going to be pretty. Like quadratic formula, right? Right, there we go. And so therefore the singular values are zero, square root of 0, and the square root of 15 minus root 29 over 2, and the square root of 15 plus root 29 over 2. Bang! Right. Oh, that's so exciting. I love it when things work. Cool. Whatever they are. I don't know what they are. So you know how it says we have to square root them? Does that mean that the eigenvalues of A transpose A always work out to be positive? I reckon it must mean that. All right, I've come to the end of my time. I'm going to stop there. Thank you for joining me today. And just note that the Maths Learning Centre is open all the way to the end of the exam period, including, for example, next week, if that's relevant to you. Thank you.